All right. Okay. Well, my clock says 2:15, so we can go ahead and get started. Thank you all so much to everyone in the room, as well as everyone on Zoom and YouTube, for joining us for the second press conference of the day here at the 241st meeting of the American Astronomical Society in Seattle, Washington. It is January 9th, I believe, at 2:15 p.m. Pacific. My name is Kerry Hensley, and I'm the AAS Deputy Press Officer, and I will be leading the show today. Assisting me is Ben Koss, our AAS Media Fellow in the back here, as well as Cecilia, our Astrobates Media Intern. There will be several press releases distributed associated with this afternoon's press conferences, so please be on the lookout for those on our AAS Press Twitter account, on the AAS website, as well as on our Press-Conference Slack channel. The press kit has been updated from this morning's session with links to the presentation files and press releases. The webcast video will be added later today. So a brief overview of the ground rules for this press conference. I'm going to introduce the topic of the conference and our panelists first. We're going to hear from our four panelists in the order you see them sitting. We won't break for Q&A in between the presenters, and we'll have some time for Q&A for all four presenters at the end. And a reminder to our journalists who are viewing the press conference remotely to please use the Q&A feature to queue up your questions in Zoom. So the topic of our press conference this afternoon is mergers, bursts, and jets. So we'll be looking at some energetic goings on in the universe. Our first presenter is Mike Koss from Eureka Scientific Inc. He'll be speaking on the closest separation confirmed multi-wavelength dual active galactic nuclei. Next is Vikram Ravi from the California Institute of Technology, speaking on the first results from the Deep Synoptic Array, a large sample of fast radio burst host galaxies. Next is Cecilia Chirenti from the University of Maryland, speaking on hypermassive neutron stars found in short gamma ray bursts. And our final presenter, Sirina Prasad from the Center for Astrophysics, Harvard and Smithsonian, will speak on using ALMA to observe a rare hydrogen recombination line maser emitting star. So with that, I'm going to turn things over to Mike and get our presentation started.
Thank you. Okay, great. So my name is Mike Koss. I am a research scientist at Eureka Scientific here in Seattle. And I wanted to talk to you about the discovery of the closest separation multi-wavelength dual active galactic nuclei, or dual growing black holes. So this is work that's done by an international collaboration. And so lots of co-authors. I'll mention my second author. The second author on this paper is Ezekiel Treaster. And so what I wanted to talk to you about is galaxy mergers. So I'm going to give you kind of a timeline of what happens in a galaxy merger. So we think that basically nearly every galaxy has gone through some major mergers in its past, and many have the major mergers expected in the future. And I wanted to show you a simulation here. Gotta go to the left here. Okay, so during the process of merging, you can see these two galaxies pass by each other. And there's violent disruption that's happening as the two galaxies are plunging together, and you can see tidal tails and gas and dust being flung out. And basically, we think that a lot of material is being pushed onto the centers and actually growing the supermassive black hole. So merging galaxies, we think, really fuel black holes. And at that last phase that I showed, we actually think the black holes will eventually merge and emit gravitational waves. Now, we've never detected supermassive black hole mergers. So we really want to understand what is the prequel, or the phase right before that. So one of the big questions that our study was addressing was, can we find something that's really in the final merger stage that we can resolve, because this will give us an idea of the population of galaxies that might produce gravitational waves that we can detect. Okay, so to make this detection, we used adaptive optics, and we actually looked at nearby galaxies that have very bright black holes, right? Because the merger is fueling the black holes. And so if we have these bright AGN, we thought, well, let's look at these and maybe we'll actually detect two growing black holes or two nuclei that are in the process of merging. So when we looked at this particular system, if you look on the left, that's the optical image. You can see that basically you can't see much from that optical image. You do see maybe some evidence of tidal tails, but with adaptive optics, we can improve our resolution by a factor of 20 and really look deep within the heart of this nearby galaxy. It's only 500 million light years away. And so with adaptive optics, basically we go from legally blind to perfect vision, because it's more than a factor of 10 improvement. And we see those two nuclei shown in the near infrared Keck image. Now, this is just the stellar emission. So we wanted to see if there's two growing black holes in those two systems. And these systems were separated by only 750 light years, which is incredibly small and much closer by more than a factor of 3 of any dual AGN that had been detected with multi-wavelength observations. So I should also mention, this is really at the edge of what we can do. Is a nearby galaxy, so we can really see things in detail. And this particular instrument could resolve a candle on the moon, so just incredibly sensitive. Okay, so to understand this system, we really need a variety of observations, and one of the most important ones was the millimeter emission, which we got with ALMA, which is shown on the bottom right. This array of telescope dishes with interferometry, we can get very high spatial resolutions, and we actually detected compact millimeter emission, which traces growing black holes in these two systems very close in. So this is really one of the first times we've used this to resolve two sources in the centers in this very close dual AGN. So we also got a number of other observations that help complete the story. So we had observations from Hubble. We had observations using adaptive optics actually in the optical. We had additional observations with adaptive optics in the near infrared, and also finally in the X-rays. So this particular system is really the closest dual AGN that's ever been resolved, where we've had multiple observations to confirm it. And it's more than a factor of 3 in terms of how close they are together. And so this image on the left is showing an additional confirmation. So the wide image is optical muse, which gives you broadband optical emission. And then you can take a little slice of that actually traces a high ionization emission line that's produced from AGN. And you can see it overlaps exactly where we found the two sources in ALMA, and right at the center of those two galaxy nuclei that we had seen. So we have multiple confirmations. The other thing that we can do with this wealth of data is get the stellar velocities and actually predict the masses of the black holes based on the motion of the stars. And we actually found that they are very similar masses. And so that suggests a very strong gravitational wave signature. So that's really important. So now I wanted to go to sort of the timeline to gravitational waves. So we detected this system at about 200 parsec separation, and we expect them from this point on to go through several other steps in terms of merging the two black holes. So the second step is stellar hardening. So basically the two black holes are sort of within each other's gravitational effects, but you can actually get stars coming in between them that will cause them to get closer and closer together, until we get down to the 100th of a sort of parsec, where we actually have gas driving the in-spiral and gravitational waves. So we chose this system because it's really nearby and we can achieve incredibly high spatial resolutions. But this type of system is much more common in the distant universe, where we think mergers are more common. And actually AGN, even though this was luminous in the nearby universe, it's very similar to the luminosities in the distant universe. So we think that this portends an incredibly bright future for gravitational wave detections, because we're seeing these systems in these growing black holes. So we know what type of system might be associated with the gravitational waves, because this gives us kind of a prototype. So just to give you some final notes on this system. So it's closest dual AGN detected in multi-wavelength observations. And I think it really opens up a pathway with ALMA and some of these other observations to really develop a systematic sample to try and extend it to distant galaxies. With this system, we think after 200 million years, we would get a gravitational wave emission. They would merge and create a massive elliptical galaxy. And this whole timeline is actually something that we'll see in our own galaxy, the Milky Way. Now, it is right at the beginning of the merger with Andromeda. So the whole time period will take 5 billion years, but we'll have a similar thing of the two galaxies merging together and gravitational waves as the two black holes we think will eventually merge. So the article was published today in the Astrophysical Journal Letters. I put the graphics and animations available here, and this is my contact info. I'm local here, and here's my cell phone and email. Thank you so much for your time, and if you have any questions, I'd love to answer them. Thank you so much.
All right, great. Thank you very much for joining. I am Vikram Ravi. I'm at Caltech, and I am very excited to tell you about a new radio telescope that we've built at the Owens Valley Radio Observatory. So, of course, this work cannot be done without a huge team, some of whom are in the audience today. And we've been doing some really fun stuff over the last little while that I'm really, really excited to show you for the first time. So, the purpose of this radio telescope, the Deep Synoptic Array, is to discover and precisely localize the origins of fast radio bursts. And as it turns out, the DSA is now the world-leading instrument for this purpose. And we care about this deeply because we want to understand, of course, what FRBs are, how they're emitted, where they come from, as well as use them to probe unseen baryonic matter in the universe. And so this, as it turns out, is a really hard game. In the entire history of this field, I think of the last 14 years or so, only 21 FRBs have been pinpointed to galaxies with the accuracy needed to actually identify where they come from. And these are the first 30 that were found with the DSA in just the last year. You can see a whole lot of amazing stuff here. I've ordered these galaxies in roughly an order of increasing distance from the Milky Way. So as we sort of go through the top row, you can kind of see the galaxies look fairly big, right? You have this nice big face-on spiral over here. Can you see my cursor? No? Oh, that's right. The top left shows a nice big face-on spiral, whereas by the time you get to the bottom row, it starts to become really hard to see the host galaxies. And that's because, of course, these are further away. We're probing both the very nearest as well as the very furthest FRBs. Now, of course, what are FRBs, right? We observe them as luminous flashes of radio waves from distant galaxies, and we search for them in data like these. Now, you might think, of course, there's nothing really showing up on the screen, and that's because I haven't played it forward yet. In real time, that's what an FRB looked like. This sweep of the pulse, such that it's delayed at lower frequencies, actually tells you about the amount of matter between us and the FRB source. You can measure this delay and directly convert it into a measure of the intervening matter. And this is super cool because, one, by figuring out what the environments of FRBs are like, we can say something about their origins. We care about how the sources of FRBs form and evolve, as well as the physics through which they're emitted. How do we make such luminous pulses in distant galaxies? But what's really, really exciting about FRBs, and what I'll tell you a little bit more about in a minute, is the fact that we can use FRBs to measure the amount of matter in the cosmic web. So in the simulation in the bottom left, you're seeing an FRB propagating through a depiction of the cosmic web. And as it does so, it accrues what we call dispersion, this delay at lower frequencies. And as it turns out, more than 80% of baryonic matter, not dark matter, but actual matter like you and me, is invisible in the nearby universe. And we can use FRBs and their dispersions to answer questions like how this matter is distributed, as well as how galaxies form out of this matter and in turn impact the matter around them. So to do this, the DSA needs to excel along 3 axes. FRBs occur really fast. They can last for much less than a millisecond. And so we scan the sky with a frame rate of something like 4,000 frames per second. We need to survey a large area of sky. Although FRBs occur at the rate of something like 1,000 per day, they only last such a short time that in order to catch them, you need to survey a fairly large amount of sky. We look at roughly 10 square degrees, or about 400 times the size of the moon. And to pinpoint their origins, we need an angular resolution of somewhat less than 1,000th of a degree. Now, we've been able to do this through some revolutionary technologies, one being the fact that we don't actually have to cool our receivers with liquid helium. We achieve similar performance at room temperature. And 2, we need to process a lot of data. A nice analogy is it's like streaming 28,000 Netflix movies all at once and processing them in real time. So what does this look like? Well, this is what the night sky at the Owens Valley looks like on a clear night. And that little square shows you roughly the size of sky that we survey at any given time. So this is about 10 square degrees. Now, within this area on sky, there are something like 10 million galaxies that an FRB could come from. And so, of course, to pinpoint the origins, you need to resolve it by 1 part in 10 million, which the DSA does. To do this, for example, you have to line up the signals from all the different antennas of this radio interferometer array to roughly 10 picoseconds in order to deliver this resolution. So what are we learning? Well, we have a lot of FRBs, and the team is busy working through and understanding what it all means. But one in particular is very interesting, and the paper is on the archive at this link. It actually tells us something, not about distant space, but about the Milky Way itself, the galaxy in which we live, because we were able to use this FRB to actually weigh the amount of matter in a halo surrounding the Milky Way. And we're able to say that although the universe on average has something like 16% baryonic matter, with the rest being dark matter, the baryon fraction of the Milky Way is much lower. It's likely less than 10% of the total mass of the halo. And so, of course, there's plenty of science out here. The DSA, being a new radio telescope, is just getting started. We've commissioned it over the past year and are now beginning science operations. This has a particularly interesting implication for the upcoming DSA 2000 radio telescope, and I encourage you to visit our booth in the exhibition hall as well. We've used 1 FRB from this sample to measure the mass of the Milky Way. And to hear about some of the other amazing science that's being done, please come to our special session tomorrow at 2 o'clock as well to go through the whole range of things that we're doing. My contact details are there, and thank you very much.
Okay, so good afternoon. Thank you all for being here. My name is Cecilia. I'm from the University of Maryland, and I'm going to be telling you about how we found 2 hypermassive neutron stars using short gamma ray bursts. Our paper was published today on Nature. We're very happy about that. and we are a very small team of 5 people. One of the co-authors is Cole Miller, also from the University of Maryland there in the back. Okay. So in this story, I'm going to be interested in the interplay between neutron stars, gravitational waves, and gamma ray bursts. Now, sorry, presenting with the mask is always a little bit hard for me. My apologies. Now, we know that when binary neutron stars in spiral and merge together, they emit gravitational waves with increasing frequency, and that's what I'm calling the whoop here. And at some point, they also emit a gamma ray burst, which appears in this video with a ding. And you guys didn't hear anything at all. Is there any way to fix this? Because it's rather important. Sure. Yeah, it's not really important for this slide, but I have another video later on where I would really, really want to have the sound going. Oh, well. In that case, I'm going to have to do the special effects later on for you guys. My apologies, and thank you for your patience. Okay, so between the whoop that you didn't hear and the ding that you also didn't hear. Thank you. A hypermassive neutron star may be formed. Now, a hypermassive neutron star is exactly what it sounds like. It's going to be more massive than a neutron star has the right to be. It's going to live just very briefly for less than a second before it collapses to a black hole, and there is no escape. It is going to collapse to a black hole. It just hangs in there for this brief time because it is spinning just so fast. And it is going to be about 20% heavier than the heaviest pulsar that we know, and it's going to have a size about 2 times the size of a typical neutron star. While it's rotating and jiggling and shaking, it's also emitting gravitational waves in kilohertz frequency, and that is unfortunately too high for current gravitational wave detectors. Now, I'm going to be looking for the signal of the hypermassive neutron star, and here I need to make an important distinction between a periodic signal that has a single frequency, is like a pulsar, it's very easy to detect, and a quasi-periodic signal. Now, a quasi-periodic signal is harder to detect, it's messier, because it has maybe lots of close frequencies, dissipation, or time variation, so it's not such a clean signal. Okay, in the case of a hypermassive neutron star, what we have is exactly a quasi-periodic signal. These quasi-periodic oscillations, or QPOs for short, are what we're going to be looking for. And what it looks like, if you want to visualize it, is kind of like a messy damped mass spring system. Okay, so we looked for this in more than 700 short GRBs that we have analyzed from archival data, from SwiftBet, from EGBM, and from BETSI. And in each case, we took each one of these short GRBs, cut it into smaller pieces if necessary, and for each one of those, we analyzed whether it was best described by a noise-only model or by a noise plus QPO model. Now, nothing really is showing up here in the Swift and in the Fermi data, but maybe there is something there in the BETSI. So we would like to take a closer look at it. And BETSI actually was an instrument in the Compton Gamma Ray Observatory, one of NASA's great observatories in the 90s. And for our analysis, BETSI was an amazing instrument because of its large detector area and great timing capabilities. And this is where we found our signals. When we focused on the high energy data from Betsy, we have these two very clear outliers here. These are our signals. In these two cases, the noise plus QPO model is overwhelmingly preferred. And in both cases, we have two QPOs each with very similar frequencies between the two of them, and very good agreement with the simulations that show a hypermassive neutron star. Now, here, I'm going to show you a simulation of a binary neutron star merger. On the left, you're going to see the frequency of the simulated gravitational waves. Their frequency is going to increase here down along this axis. And at some point, you're going to see the light curve of the GRB starting to go. Now, here is where I really wanted to have the sound effects for you. And I guess I'll just sing it as it goes. Ooh. Thank you. So what you saw there was the whoop of the spiral. I just couldn't hold my breath enough to make the long spiral. Apologies. And when the hypermassive neutron star was formed, you have this jump in the frequency, the pitch changes. There goes the and then the black hole is formed. Okay, so this is what we think that has happened. I know that I'm going a little bit over time, but this completely threw off my timing. So our signals, they are consistent with a hypermassive neutron star as seen in numerical relativity simulations. The signals have two QPOs. The first one has a high frequency of approximately 1 kilohertz and a lower amplitude. The second one has an even higher frequency of about 2.7 kilohertz and higher amplitude. And that is the one that is very important because it also could give us information on the composition of the neutron star. Now, compared with other neutron stars, the hypermassive neutron star spins way faster than anything we know of in the universe, almost 2 times the spin of the fastest known pulsar. And the way we understand these events, they should form a black hole in about 10 milliseconds. So that's faster than the blink of an eye, and that's how long that hypermassive neutron star lives. Okay, so to summarize, between the whoop and the ding of a binary neutron star merger, a hypermassive neutron star can be formed. We looked for signals of this hypermassive neutron star in short gamma ray bursts, and we found 2 of them. And we cannot see this yet with with gravitational wave detectors, but we will be able to see them in gravitational waves with the next generation of detectors in the 2030s. And in the meantime, we'll keep looking for them in gamma rays. Thank you so much.
Okay. Hi, everyone. My name is Sirina Prasad, and I'm an undergraduate at Harvard University. And today I'll be talking about our study of a rare hydrogen recombination line maser emitting star. I should say my main collaborator and mentor, Chicho Zhang, is here in the audience, and he'll join me for the Q&A afterwards. Okay, so the name of the star is MWC349A. It's one of the stars in a binary system in the constellation Cygnus, and most evidence suggests that it's a massive evolved star. So on the right here is an image of the area around MWC349A from the Spitzer Space Telescope. And you can see that it's surrounded by a roughly hourglass-shaped nebula. In the center of that image, there is the star. So MWC349A is a really unique system because it has hydrogen recombination line masers. A maser is a natural source of strong radio emission, kind of like a natural laser. And they're formed when you have population inversion of hydrogen transition. So when the hydrogen ions recombine, they emit radio waves. This is not a very common phenomenon, but it's extremely useful because it gives us a way of tracking things in the system. So if the masers are in, let's say, like a wind, and they're emitting radio waves, then you can see the movement of that wind by tracing the radio emission from the masers. And so that's exactly what we did with MWC349A using observations from ALMA, the radio interferometer in Chile. So this kind of study has been done with MWC349A previously, but it was done with the SMA, the submillimeter array in Hawaii instead of ALMA. So the main finding of that previous study was that there are two groups of masers in the system. The first group are the disk masers that lie in the star's circumstellar disk. And the second group are the wind masers that lie in a rotating, expanding wind that's thought to be both above and below the disk. So the data from that study is here on the slide. On the left is the spectral profile of the hydrogen recombination line with velocities that range from -40 to 60 kilometers per second. And on the right is a plot of the positions of those masers. So on the right, you can see that in the center, along the east-west direction, there's a very rough linear structure, and those are the disk masers. And then above and below that structure are the wind masers. But just by looking at this image, it's kind of a vague picture of what's going on in the system. It's not very clear. The disk is kind of a rough linear structure. The errors are kind of big and they overlap, and it's hard to distinguish between the wind and the disk masers just by looking at this. And that's because the precision of this study was limited by the angular resolution and sensitivity of the SMA. So to improve this, we took data with ALMA in its most extended configuration, and we achieved a much higher angular resolution for a more accurate mapping of the masers. So first, the continuum data. In the center here is the 1.4 millimeter continuum image of MWC349A. And the most prominent thing about this image is that there's an hourglass shape. So that hourglass shape has been seen in the continuum of MWC349A before, but this is the first time that we're resolving it in this wavelength. And the shape basically comes from the wind. So in the circumstellar disk is where the waist of this hourglass is, and then the rest of the hourglass shape is where the wide-angled rotating wind is. Another interesting thing about this image is that the nebula, the surrounding nebula that we saw in the Spitzer image is also hourglass shaped. So these two hourglass structures are not the same thing. It's kind of like an hourglass within an hourglass because the continuum image is much more zoomed in. But it's an interesting likeness that we see an hourglass in both of these, on both of these scales. And there may be more to uncover there. So now for the masers, we studied two maser transitions, H26 alpha and H30 alpha. So on the left here is the spectral profile of those two transitions, and the velocities here go from -85 to 100 kilometers per second, which is more, it's almost twice the range of the SMA study. So already we see an improvement in data quality. So to estimate where the positions of these masers from the images that we obtained from ALMA, we assume that at each wavelength, so at each velocity in the spectral profile, we have a point source, and then we fit a two-dimensional Gaussian to each image, and the center of that Gaussian is our estimate for the position of the maser. So on the right of the slide here is a plot of those maser positions. And just by looking at it, you can see that it's much more precise than the SMA study. You can see a very clear linear structure in the center, that those are the disks. And then even the masers that are above and below the disk lie in well-defined lines with small errors. So this precision is really quite remarkable, and it comes from the increased sensitivity and resolution of ALMA. Okay, so the maser distribution tells us a lot about what's going on in the system. So the most prominent thing here is the disk in the center along the east-west direction. It confirms the inclination angle of the disk to be 9 degrees, which is in line with previous studies. And we also see that the H30 alpha masers extend further in radius than the H26 alpha masers, and that's what we would expect based on previous studies. There are also masers rising above and below the disk, and those are the wind masers. But the most interesting thing about this image are the masers along the polar axis in the center there. That kind of thing has never been seen before in this system. And those masers have line of sight velocities between 50 and 90 kilometers per second, negative and positive. So the interesting thing about those velocities is that those are only in the line of sight. So there's another direction of velocity. There's another direction in which the masers can be moving. So when you correct for that, using the inclination angle of the polar axis, you get that the space velocities of those masers along the polar axis can reach 500 kilometers per second or more. And that's extremely fast. That's too fast to be produced by photoevaporation, which was the theory for how these wind masers are produced, was by photoevaporation. So that implies that these masers along the polar axis are not part of that wind, but instead they're part of a jet. A jet makes the most sense here because these are high velocity masers along the polar axis here. And based on what we know about other systems with jets, the most likely scenario is that the magnetic field from the star is forming, collimating, and launching the jet. So just to give you an idea of what this might look like in space, this is one artist's rendition of what's going on. The exciting thing about this finding of a jet is that it would be the first time that we're seeing a jet like this, a collimated jet, around a massive evolved star. So we see jets around young stars all the time, and even around some evolved stars, but not anything this massive. So MWC349a has an estimated mass of between 30 and 35 solar masses, which is larger than we've seen for a system with a jet. So this opens up many new avenues of investigation, like why and how the jet forms and how it interacts with the rest of the system. So just to leave you with a few key notes, we spatially resolved an hourglass structure in the 1.4 millimeter continuum for the first time. We found that masers are distributed in a Keplerian disk and in an ionized wind, both above and below the disk. And then we also found the first evidence for a collimated jet along the polar axis. So that's it. Thank you.
All right, we can get started with our Q&A, and I want to welcome to the stage Sirina's collaborator, Chijo Zhang, also from the Center for Astrophysics. So for the people here in the room, be sure to raise your hand so Zili can bring you the microphone. Please be sure to state your name and affiliation and who your question is for. And if you're on Zoom, please be queuing those questions up with the Q&A feature.
Hi, I'm Ethan Siegel from Starts with a Bang on Big Think. I have two questions. First is for Cecilia. Thank you. This was really interesting. I wanted to know, based on what you've seen, because you only have gamma ray data, you don't have gravitational wave data for this hypermassive neutron star. Do you have any prospects for reconstructing the mass or the spin or other properties of the post-merger HMNS or the progenitors that gave rise to it? And my second question is for Michael. Michael, I want to know, you said after 200 million years, you said UGC 4211 will merge and produce an elliptical galaxy. And that second part is very surprising to me because over the last 20 years, we've learned that most spiral-spiral mergers don't produce an elliptical, but rather lead to a gas-rich galaxy that will still contain a disk. So can you tell us why we expect UGC 4211 to become an elliptical galaxy post-merger?
So thanks for the question. And we would love to get all of that information, but with the data that we have, we can't. And one reason for that is that Betsy, the old detector, wasn't very good at localizing the direction of the source of the GRBs. So we don't have the direction, we don't have the redshift, we don't have the correction to the frequency that we have seen. The frequency that we see could have been redshifted, so the frequency could have been higher. There are relations that have been observed in numerical simulations that allow us to learn about the equation of state of the neutron stars and the spin of the hypermassive neutron star. But in order to use those more precisely, to the extent that the simulations are precise, we would need to know the redshift. So we can only, for example, put some limits here.
Yeah, so that's a really great question. What would it look like after it finally merges and settles down? So this particular system, you could see it a little bit on the optical image that I showed on the left, but the spiral arms really are not prominent in this kind of final merger stage. And also the stellar mass range it's in is kind of on the more massive end. So where we might expect something like shells or other things like that, as opposed to, prominent spiral arms. But, it's not a gas pore system. So, and this is actually interesting because some of the predictions thought they would be in these kind of red and dead massive ellipticals would be where we would see gravitational waves coming from. But this source actually, it has an AGN, it has a significant reservoir of gas. So it is really interesting. And we probably have to think a lot about, how bright and how long if it could, sort of regenerate some spiral arms. But that's a really interesting question to think about.
Govert Schilling, freelance from the Netherlands. I have brief questions for the first three presenters. For Michael, do you think that gravitational waves from UGC 4211 might be observable with a future LISA space observatory? And for Vikram, could you briefly describe or say something about how the DSA compares to the CHIME observatory in terms of USPs? And for Cecilia, I was wondering, you said the QPOs were found in the Betsy data, not in Fermi and Swift data. Is that just a coincidence, or could you in the future find future QPOs in Fermi and Swift data?
Okay, yeah. So the black hole masses that we measured were a few times 10 to the 8th. So the interesting thing is, so LISA is a space-based gravitational wave detector, and then you've got pulsar timing arrays, and it's sort of right in the range or at the edge of both of their detections, where they're less sensitive, but you still might be able to detect sources like this. I think LISA would be the best one, although not to as high a redshift as some lower mass black hole mergers. So,
yeah. And thanks for the question. So CHIME is a little bit more sensitive than we are and sees a lot more of the sky, about 20 times, but cannot localize with anywhere near the accuracy. And so although CHIME sees somewhat more than an FRB per day, and we see something like 1 per week, our localization accuracy is about a factor of, let's say, 600 times better.
So about the comparison between the different detectors, Betsy was definitely the best instrument for this type of analysis because of the larger detector area. But since we found those first two signals, we have understood the data a little bit better. So for example, the signals became clearer when we looked only into the higher energy data of Betsy. And that's something that we have not yet done for the Fermi data that we have analyzed. So that's something that we want to do now in the future as well. So there could be more signals hiding in the data that we have already analyzed from Fermi and Swift.
Okay, go ahead. Hi, I'm Zilly from Astrobytes. I have a question for Vikram. So you mentioned that one of the science results was using the dispersion measure of FRB to probe the mass of the baryons in the Milky Way. So I assume that one FRB gives you one sightline. So are you assuming spherical symmetry to get to the total mass? And can you elaborate on whether that's a reliable assumption? Thanks.
Yeah, great question. So yes, we are using one FRB, and if you do use one FRB, you absolutely do need to assume spherical symmetry. We do cross-check our results against a couple of other sightlines, one being the Large Magellanic Cloud, which has pulsars, and you can use their dispersion measures to give you a separate constraint. You can also use, as we did, the globular cluster M53, which sits about 18.5 kiloparsec off the plane, and that gives you a third sightline. There is another FRB in a globular cluster of M81, which gives you a fourth sightline, and these all sort of agree and give you a roughly similar constraint. And so, yeah, although you're absolutely right that spherical symmetry may not be the case for these halos, there might be streams left by infalling dwarf galaxies. There might be outflows driven by some sort of star formation or perhaps pre-existing AGN activity in the Milky Way. It seems like the constraints are all sort of agreeing.
Great. I think I saw a hand in the back here. Maybe that question was retracted. No, okay, one back here and then back up to Charles.
Corey Powell, freelance. Following up on that previous question, this number that you inferred of a 10% baryonic fraction, of sort of an unusually low fraction, how surprising is that? And does that give you any kind of constraints on other models of the Milky Way halo?
Yeah, so it's surprising in the sense that for a fair while, at least within the FRB community, we assumed that halos kind of keep the cosmic fraction of baryons that we would expect. However, certainly it's been the case that numerical simulations of galaxy formation show that various feedback mechanisms tend to remove mass from halos like the Milky Way. For example, AGN can blow mass out, as can winds from massive stars and supernovae. And so the constraint of less than 10% of the mass being baryons is not surprising in the context of those simulations, but it does suggest that such mechanisms are at play.
Great. And then Charles, do you still have a question up here?
Hi, Charles Blue with Norlab Communications. Sirina, can you or your colleagues speculate on why we have this collimated jet on an evolved star when it seems more of a characteristic of a protostar? And what business does it have being there?
So the one of the peculiar characteristics has a disk, and that probably is where is driving this jet. And as to how this disk, why this disk form, there are sort of a number of hypotheses, and one of them actually is the being in binary, because the plane of the disk actually is aligned with the secondary objects, which is also a massive star. It's MWC 349b. It's about 2.4 arcsecond in projected separation. So that might have been why you have a disk, but I think this is one of the puzzles that we try to understand.
Great. Do we have any questions online right now? Nope. Are there any other questions in the room? This is your last chance to have these 5 people here at the same time. Well, if not, we can end things a few minutes early. Thank you so much to all of you for joining. And thank you as well for the PIOs who worked to put together press releases. Our next press conference will be tomorrow, Tuesday, January 10th at 10:15 a.m. Pacific time. We will be discussing new developments in the world of planets. So let's thank our great speakers one more time before they go.